Our previous discussion about the hyperbolic planes and isotropic spaces now allow us to finally describe the Witt decomposition. So any regular quadratic space has the following decomposition. This is a direct sum of hyperplanes and then with an anisotropic part. A natural question is this decomposition unique? Well, it turns out this number k here is independent of the specific decomposition, and we call it the Witt index of V. This VA here, the isometry class of VA is uniquely determined by V. This is due to Witt's cancellation, which we'll discuss later, and this is called the anisotropic part of V. The Witt decomposition is going to come from the following proposition. We'll prove that proposition in a moment, but right now let's see why it implies the Witt decomposition. The proposition says that if we have an isotropic regular quadratic space, then it can be written as a direct sum of a hyperbolic plane with its orthogonal complement. Thus, given any regular quadratic space, if it's already anisotropic, then we're done. If it's not, if it's isotropic, then we use this theorem to get out a hyperbolic plane part. And then we apply that proposition again to W to get out another hyperbolic plane until we get to an anisotropic part. But wait, why does the proposition apply to W? Why is W a regular quadratic space? Actually, in general, if we have an orthogonal decomposition of a regular space, then each of the components must be regular, and let's see why. Let's find out what the radical of W is. Actually, let's show that it's actually 0. So, let x be in the radical of W. What does that mean? That would mean that x is orthogonal to everything in W, but because x lies inside W, right? It's in the radical of W, so it lies inside W, then it must be orthogonal to H, because H is orthogonal complement of W, and so x must be orthogonal to the whole of V, so x must lie inside the radical of V, but the radical of V is 0 because V is regular, so then x must be 0, and thus W must be regular. So we can keep applying the proposition to W and then get a hyperbolic plane out of W and keep going on until we get to an anisotropic part. And this gives us the Witt decomposition. So it remains now to prove this proposition. So let V be a regular isotropic quadratic space. We want to find a hyperbolic plane inside it. Observe that it suffices to show that V contains some binary isotropic space H, which is regular. Why is that? Because if V contains some binary isotropic quadratic space H, then by our previous discussion, H being binary and isotropic must be hyperbolic, so it must be a hyperbolic plane. Now, then if additionally H is regular, we must have a decomposition then of V into H direct sum with its orthogonal complement. That's just a property of regular subspace. So let's construct first a binary isotropic subspace of V. Well, now that is simple, because since V is isotropic, it must contain an isotropic vector. So for H to be isotropic, we just need to let H contains this isotropic vector, then it's automatically isotropic. Now, to make this binary, we just need to take a vector linearly independent from V. Well, how do we know there must be a vector linearly independent from V? What if this big vector space V is just equal to the span of little v? Well then, because the norm, the quote-unquote norm of V is 0, that means V must be orthogonal to itself and thus orthogonal to everything in span V. So in that case, then if the vector space big V is just span of V, then it must not be regular because its radical contain little v, so that would be a contradiction. And so the vector space big V must contain some vector linearly independent from V. It must have dimension at least 2. Right, so we can find this W linearly independent from V. And this space H must therefore be binary and isotropic, so it must be a hyperbolic plane. Now, why is H regular? Well, this is simply because discriminant is gonna be -1. It's not 0, so it must be regular. But if you don't remember this property about the discriminant and regularity, then we can see it directly this way. So suppose that H has this gram matrix in the basis V1, V2. That means V1, B of V1, V1 is 0, B of V1, V2 is 1, and so on. So this means that if we have any vector in H, right, we can write it as this linear combination. We can recover its coefficient alpha and beta by taking the bilinear form, applying to that, and then with V1 and V2. So if we have, so let's find the radical of H. Well, if a vector alpha V1 plus beta V2 lie in the radical, then both of these has to be 0. And so both alpha and beta must be 0, so the original vector must be 0. And we see then that the radical of H must be 0. So H must be regular. And now since H is regular, we have an orthogonal decomposition of V into H direct sum with its orthogonal complement. Thus we have shown that every regular isotropic quadratic space can be decomposed in this way, and if we reapply this proposition to W, we'll get the Witt decomposition, that every regular quadratic space can be written as a direct sum of orthogonal hyperbolic plane and then within an isotropic part.